Here is a task to get the lesson started. Consider the polynomials f of x equals x squared plus 1 and g of x equals 4x plus 5 with real number coefficients. Part A, compute f of 2 and g of 2 and then find their sum. Part B, compute f plus g of 2. In other words, first add the polynomials, then evaluate the sum at x equals 2. Part C, compare the answers in parts A and B. And part D, do likewise with multiplication. So if you could pause the video and work on these problems, and we will go over them shortly. And here are the answers. We find that for addition, f plus g of 2 equals f of 2 plus g of 2. We get 18 equals 5 plus 13. So it doesn't matter whether we first add the polynomials and then evaluate the sum at x equals 2, or evaluate each polynomial separately at x equals 2 and then add those numbers. We obtain the same result, namely 18 in both cases. And we can say the same thing with multiplication. And in fact, these relationships hold for all polynomials f of x and g of x in R bracket x, not just the ones we used in this task. But I'll leave it up to you to prove this more generally. In discussing this task, we said it doesn't matter if we first add the polynomials and then evaluate at x equals 2, or evaluate each polynomial separately at x equals 2 and then add those numbers. If that sounds familiar, it's the kind of thing we said when we studied group homomorphisms. And it turns out that what we have in front of us is an example of a ring homomorphism. So let's make this more explicit in the next slide. We define the function theta from the polynomial ring R bracket x to R, where theta of f of x, where f of x is the input into the function, is equal to f of 2. Now this is called the evaluation map since we're evaluating each input polynomial at x equals 2. For example, if the input polynomial is f of x equals x squared plus 1, then theta of f of x is equal to f of 2, which is 5, because it's 2 squared plus 1. Here's a relationship that we found in the opening task. F plus g of 2 equals f of 2 plus g of 2. And using our function theta, we can rewrite that as follows. On the left-hand side, we have theta of f of x plus g of x, which means first add the polynomials and then apply theta, or evaluate the polynomial sum at x equals 2. And this is the same as f plus g of 2. And on the right-hand side, we have theta of f of x plus theta of g of x, which means apply theta to each polynomial separately, or in other words, evaluate each polynomial separately at x equals 2, and then add those numbers together. Now that's equivalent to f of 2 plus g of 2. Similarly, we can express the multiplicative relationship that we found using theta. So theta of f of x times g of x equals theta of f of x times theta of g of x. So theta satisfies these two relationships, the additive one and the multiplicative one. And therefore, theta is an example of a ring homomorphism, which we will formalize in the next slide. One remark about the evaluation map is that there's nothing special about 2 here. We could have used any real number to define the evaluation map, such as -7 or pi, for instance. Here's a definition. Given rings R and S, a function theta from R to S is called a ring homomorphism if both addition and multiplication are preserved. In other words, for all elements A and B in the domain R, we have the two relationships theta of A plus B equals theta of A plus theta of B, and theta of A times B equals theta of A times theta of B. Now in the evaluation map that we just saw, the domain is the polynomial ring R bracket X, and the codomain is the field of real numbers. The following diagram depicts the relationship theta of A plus B equals theta of A plus theta of B. Here we can first add A and B in the domain R and then apply theta. That gives us theta of A plus B. And in fact, let's label up here this addition symbol with subscript R to denote the fact that this sum A plus B is occurring in R, and then we apply theta to it. Or we can apply theta individually to A and B, get theta of A and theta of B, and then add those outputs in S. That gives us theta of A plus theta of B, and let's label this with a subscript S to denote that the sum there is happening inside S. And we obtain the same result. And that's what we mean when we say theta preserves addition. A similar diagram can be drawn for the multiplicative relationship that we have here. And let's just label the multiplication symbols with subscripts R and S in the similar manner. To summarize, a ring homomorphism preserves both addition and multiplication as expressed by these two relationships. Now please pause the video and work on day 31 classwork. And afterwards, we will review some of the problems and concepts. In the classwork, we studied the reduction map phi from Z to Z5, where phi of A equals A mod 5. So for example, phi of 17 would be 2, because 17 mod 5 is 2. And we saw that phi is a ring homomorphism because it preserves both addition and multiplication. Now, we define the kernel of phi as the set of elements A and Z such that phi of A equals 0. In other words, the kernel contains elements of the domain Z that map to the additive identity of the codomain Z5. Now, the codomain Z5 is a ring, so it contains two identities, the additive identity 0 and the multiplicative identity 1. So it's natural to ask, why do we focus on the additive identity when defining the kernel? And it's because every ring is a group under addition. So by defining the kernel this way, we can use what we've already proved about the kernel from our study of groups, as we'll see below. For our homomorphism phi, its kernel is 5z, or the set of all multiples of 5. These are precisely the integers that reduce to 0 mod 5. Moreover, 5z is an additive subgroup of the domain Z. In other words, 5z is closed under addition, contains the additive identity 0, and contains additive inverses of its elements. From group theory, we also know that the kernel is a subgroup of the domain, and here, phi can be viewed as a homomorphism from an additive group Z to an additive group Z5, because once again, every ring is also an additive group. But be careful, because 5Z is not a subring of Z, because the multiplicative identity element 1 is not contained in 5Z. So once again, 5Z, although being an additive subgroup of the domain Z, is not a subring of the domain Z. Here is another observation about the kernel 5Z. It satisfies what's called the product absorption property. Namely, if R is an element of the domain Z and A is in 5Z, then the product R times A is also in 5Z. Here is a visual depiction of product absorption. We have the element A, which is already in 5Z, and the element R, which may or may not be in 5Z. It's just an element of the domain Z. And notice how the element A absorbs the element R into set 5Z when we multiply them together. To summarize, 5Z is an additive subgroup of Z and satisfies product absorption. Therefore, 5Z is an example of what's called an ideal of Z. And please see chapter 31 in the textbook for more details about an ideal of a ring. This theorem generalizes what we observed about the reduction homomorphism phi. The theorem states, let theta from R to S be a ring homomorphism with kernel K as defined. If the element R is in the domain R and the element A is in kernel K, then the product R times A is also in K. In other words, the kernel K satisfies the product absorption property. That's what this theorem is saying. And also note that K is an additive subgroup of the domain R, which we already proved in group theory. Thus, we can say that the kernel K is an ideal of the domain R, which is what we said about 5Z in the previous slide as well. Here is a visual depiction of the theorem. Notice that the element A is in kernel K because theta of A is the additive identity of the codomain S. In other words, 0 sub S. The element R may or may not be in the kernel. It's just an element of the domain R. And we want to show that their product, R times A, is in the kernel. In other words, we have to show that R times A also maps to 0 sub S. And that's what we're going to show in our proof. And now we're ready to write the proof of this theorem. Let's begin by identifying our hypothesis and conclusion as usual. And that gives us the first line of the proof and our very last line. Now, in order to show that R times A is an element of the kernel, as we discussed in this picture, we need to show that R times A maps to the additive identity of S. In other words, 0 sub S. So let's apply theta to R times A and see what happens. So we have theta of r times a. Now, because theta preserves multiplication, this is equal to theta of r times theta of a. Now, what can we say about this? Well, a is already in the kernel. In other words, theta of a, as we can see in this picture, is equal to 0s. And in fact, let's write that early on in the proof. And so here we can say then theta of a is equal to 0 sub s, since we'll be using that right here. And so we have theta of r times 0 sub s. That's where we use theta of a equals 0 sub s. But then any element of the codomain s times 0 sub s is equal to 0 sub s. And so we can say hence theta of r times a is equal to 0 sub s, and thus r times a is an element of the kernel. And that's the end of our proof, and also the end of this lesson. So I will see you next time.